Okay, so I was asked about two questions. Number 49. The reason you can see just by looking at the graph, when you look at that interval from 0 to pi, that's not differentiable, so we can't do the mean value theorem. And then I was asked about number 51. So 51, I'll make this a little bigger here. So on 51, you were given this interval from 1 to 2, so you find the endpoints. 1 when you plug it in, comma 0. 2 when you plug it in, comma 2. Find the slope 2. So the question is, when will the derivative equal 2? So you find your derivative. And right here, I set it equal to 2. You know, this is one of those, this is that, what, log base 2 of x. So you got to remember that when you do the derivative, it's 1 over that thing, and in the denominator, you have to multiply by the natural log of that base 2. So I was able to get it down. I don't know. Does that make sense?
Yep, that's most. I had most of that. Just didn't have the numbers.
Okay.
So that works.
Nadia, any questions?
Actually, the ones I had were the ones Travis had of 49 and 51.
Oh, well, that was economical. All right. Well, let's go to the new lesson. This is really pretty easy. Increasing and decreasing functions. And I mean, when you think about it, when you have a graph, it's easy to tell when a function's increasing, it's going uphill. It's easy to tell when a function's decreasing, it's going downhill. Now, more formally, when a function's increasing, what will its derivative be? Positive slope to the tangent line. Here, let's look at the, yeah. So when you look at this illustration, I mean, when the slope of the tangent line is decreasing, that means when the slope of the tangent line is negative, it's decreasing. When the slope is constant, the function's not going up or down, it's constant. And when it's a positive, it's increasing. It's as simple as that. So the idea here is, where are those breakpoints, like where those dotted lines are? So what we're going to do is, well, that's when the derivative is usually 0. And so we're going to find good old critical points again, and we're going to use the critical points as dividing lines, and then we're going to look at each section on the sides of the dividing lines. That's pretty much the plan of attack. So let's take a real easy problem here. The function f of x equals x squared. Its derivative, of course, is 2x. When is it 0? Only one time when it's 0, right? When is the first derivative 0? When 2x equals 0, and that's when x equals 0. So we know that this is divided only into 2 parts. So on your graph, we just found this is kind of the dividing point here at 0. And when you're to the left of 0, like, for example, -1, then the derivative is going to be negative, which tells me the function from -infinity up to 0 is decreasing. And when you take a point to the right of our dividing line, f prime of +1, you're going to get a positive. And so from 0 to infinity, this thing is forever increasing. So these are the guidelines. I've pretty much outlined them already, but if your function is continuous on the interval from a to b, and if it's differentiable, same old things. Number one, locate the critical numbers, and then use those to kind of those kind of are fence posts for the separate parts of the graph you're going to use. Number two, determine the sign of the derivative at a test value in each of the intervals. And then, hey, if it's positive, it's increasing. It's negative, it's decreasing. So let's look at our second example here. So we've got this function 1/2 x minus sine x, and the interval is from 0 to 2 pi. Okay, so we take our derivative, and we get 1/2 minus cosine. When is that 0? So this is finding the critical values. Well, when cosine is equal to 1/2, and the cosine is equal to 1/2 at those two angles, pi over 3, 5 pi over 3. Okay, so those are kind of our fence posts. And by the way, do we have any possibility here for the derivative to be undefined? There's no problem here.
No.
We don't have any division by 0 or anything like that. So we've got our critical points, pi over 3, 5 pi over 3. So then you kind of set up those as, I guess I call them fence posts. Pi over 3, 5 pi over 3. Okay, pick an angle somewhere. So you've basically got three portions this is divided into. To the left of pi over 3, between pi over 3 and 5 pi over 3, and to the right of 5 pi over 3. So then you just pick a test value, some value that's less than pi over 3. They pick pi over 4. Okay, what's the derivative at pi over 4? Look right below it. So at pi over 4, we got to go back to we don't have the whole function here. At pi over 4, you can substitute in, and you can find out that you get a negative derivative. Therefore, for that interval, it's decreasing. At x equals pi, which is somewhere between 1/3 pi and 1 2/3 pi, what happens there? F prime at pi is positive, so it's increasing. And finally, the last. So you got to go back to the original function to test those. Let's go back and plug in pi. So you'd have here 1/2 pi minus the sine of pi. And what's the sine of pi? Sine of pi is 0. So you'd have 1/2 pi, which is positive. And so now we know in that interval it's increasing. So it's actually pretty simple. Here's what the graph actually looks like. We found our two values of 5 pi over 3 and pi over 3. By the way, this is pi over 3 over here on the left. And when we were to the left of pi over 3, remember we got decreasing? Sure enough, see it's decreasing. When you go between pi over 3, I should write pi over 3 on there. They didn't do that. So this is pi over 3. So when you're to the left of that, it's decreasing. When you're between pi over 3 and 5 pi over 3, it's increasing. And after pi over 3, it's decreasing. And that's what we found in our analysis. So one more time, you want to find your critical values. Those will probably give you these lows and highs, you know, those max and mins. And then, all right, to the left of the first one, look at that. Then look at the part between them and look at the part to the right of it. And all you have to do is pick a test value, any value in the interval, and you can tell. Why are we assured that there's no others? Because if you did a good job of finding the critical values, there can be no other change from increasing to decreasing than what we've already found. Here's another one. Apply the first. So we've got the function x to the fourth plus 1 over x squared. Rewritten, x squared plus x to the negative 2. Well, I'm sorry. Yeah. So what they did is they divided it out. X to the, so this is like, what they didn't show this, but what they really wrote is this. They said x to the fourth over x squared plus 1 over x squared is another way to write this. Well, this is x squared, and this is x to the negative 2. So that's how they got that. Okay, so then you take the derivative, 2x minus 2x to the negative 3. You rewrite it, and you want to set this equal to 0. So you notice they factored. Of course, it can only happen on top, right? You can't get, when you have a fraction, you can never get a 0 out of the denominator. So you see we have 2 times the quantity x squared plus 1 times the quantity x minus 1 times the quantity x plus 1 when it's all factored. And then what do you get for, so 2 can't be 0. X squared plus 1 can't be 0, can it? Impossible. X minus 1, that could be 0 when x is 1. It can also be 0 when, it can also be 0 when x is negative 1. Why did they have x equals 0 as a critical value?
It's undefined.
That's right. So we have basically three critical values. So we have three dividing points. And so you don't have to make a chart, but that's the idea of what you see on the right there is, all right, I've got my negative 1, I've got my 0, and I've got my 1. And then pick 3 test values. Pick something less than negative 1, like negative 2. Whoops. Negative 2. Pick something between negative 1 and 0, like negative 1/2. And for this next test value, pick something between 0 and 1, and then pick something bigger than 1. Now, test the derivative. What's the derivative at negative 2? Well, you could probably just go right here at this point, up there, and you could just plug in what's negative 2. Negative 2, negative 4. Negative 2 cubed is negative 8. Negative 2 over negative 8 is a positive 1/4. And you can see that you wind up getting a negative. Therefore, for this part over here to the left of negative 1, it must be decreasing. Anyway, you get the idea. So it's the derivative that you want to check. Take your test value and check the derivative, because if the derivative's negative, it tells you it's decreasing. If it's positive, it tells you the function is increasing. Questions? So when you get to the assignment, yeah, they do this visual thing first. So here, when you look at numbers 1 and 2, it says use the graph of f to find the largest open interval on which f is increasing. So on number 1, what's the largest interval that the function's going uphill?
0 to 6.
Yep, 0 to 6. What's the largest interval in that same one that's decreasing?
6 to 8.
Yep, you got it. How about number 2? What's the largest interval of increasing there? Increasing.
4 to 5.
4 to 5, yep.
Yeah.
How about decreasing? Let's see, it goes from -3 to +1. And this one goes from 1. So I guess -3 to +1 is an interval of 4.
Yeah.
That would be the biggest decreasing one. Yep. Okay, so anyway, that's the idea on that. All right. 3 to 8 says use the graph to estimate. Yeah, so graphically it's pretty simple, isn't it? You look at number 6. What would you say would be the intervals of decreasing?
-2 to -1.
Yeah, except that graph probably goes on forever to the left, so I'd say negative infinity to -1.
Sure.
And then from
0 to 1.
Yep, increasing
-1 to 0.
and
1 to infinity.
yep, that's the idea. So those are pretty simple. They're just visual. Okay, let's go on to this next part. So it says, applying the first derivative test, find the critical numbers, like we just did. Find the open intervals on which the function's increasing. Okay, like we did. And then apply the first derivative test. And then it says, go ahead and pull out Desmos or your graphing calculator to confirm. So we didn't, you can just, I think that's good to check. Is it really decreasing from such and such to such and such? So that's what that section's about. You do have to be a little, there are a couple piecewise functions here at the bottom of this section. So you got to remember on a problem like that, you actually have a graph in 2 parts. But you can see. So let's see. Let's do a couple more here. How about, so here's 4.3, number 17. So is that one on this? That's in this group. I don't know where 17 is. Here, let's take a look. 4.3, number 17. So the directions there are down here. In 9 to 20, identify open intervals. Oh, so it's just find the increasing and decreasing intervals. So 17 is e to the x, e to the negative x plus e to the 3x. So there's our function. Find the derivative. Does that derivative look correct to you guys?
Yeah.
Yeah. Set it equal to 0. So we're trying to find the critical numbers. Looks like I only found one at -0.27. So what I didn't do now is the last part. Let me just go back to the directions here. 17. Yeah, so the thing I didn't do is, so we only have 1 point here. So that means we just have 2 intervals, right? To the left of -0.27 and to the right of it. So then you would go back to our derivative here, plug in about, to the left of this. How about we could do like -1. Okay, what happens when you plug in -1 up here? Well, negative x would be +1. So you get -e. And then on the second part, you're plugging in a -1. That's +3e to the minus 3 power, which is negative e plus 3 over e to the third. So on the bottom, I mean, that's, yeah. So what's going to happen? We got a negative e, so negative 2.7 approximately, plus 3 over, plus a small fraction, so that one's going to be negative. So the interval to the left from negative infinity up to negative 0.27 is going to be decreasing. And anyway, so that would be one, another one like that. Number 19, let's take a look at that one. The function is x squared times the natural log of x over 2. So, product rule, first times derivative of second. Chain rule, let's see, first times derivative of second. So the derivative of the second is the reciprocal of x over 2, 2 over x. And then we have a chain rule, 1/2 x, the derivative is 1/2. And then plus the second times the derivative of the first. Okay. Well, after, I was able to locate critical values, 2 of them, one at 0 and one at 2 over the square root of e. 2 over the square root of e is about 1.213. So I got these 2 dividing points. So what's to the left of 0? Negative. And I said can't be. Why did I say that? Because you can't take the natural log of a negative number. And you can see in the original function, so if I had like a negative 1, for example, that's the natural log of negative 1. You can't do it. So that's out. So we don't have to worry about that. So that function doesn't even go over there. Now I'll pick a number between 0 and 1.213. Like 1. And then anyway, I found out it's decreasing in there. I found out it's increasing over here. Formally, I guess I should write it out. Instead of leaving it like that, I should write my answer like, I think this is what the book is expecting, that you write this like this. Decreasing from 0 through 2 over the square root of e, and increasing from 2 over the square root of 3 to infinity. I think that's the format they have in the back of the book.
Okay.
And let's look at number 28. So 28, we have this problem, and we first need to find the critical points. So we've got to take the derivative. So I don't know. I guess you could say I took the easy way out. I squared x plus 2, and then I multiplied by x minus 1, and then I took the derivative, and I got 3x squared plus 6x. When is the derivative equal to 0? Well, I was able to factor that, 3x times x plus 2. When is 3x equal 0? When x equals 0. When is x plus 2 equal 0? When x is negative 2. So I found my 2 dividing points. Pick a number to the left of negative 2. I picked negative 3. What's the derivative at negative 3? Negative 3 squared is 9 times 3 is 27. 27 minus 18 is 9. So it's positive. Therefore, it's increasing. Then I picked between negative 2 and 0. I picked a negative 1. You can pick any number in between there. Negative 1 squared is 1 times 3 is 3. 3 minus 6 is negative 3. So it's decreasing in that interval. And to the right of 1, I picked 1. By the way, when you have a chance, pick numbers that are easy to calculate with, like 1, -1, 0. But anyway, I picked 1. So we're going to get what? 3 plus 6 or 9. It's positive, therefore it's increasing. And then here's where I wrote it out properly on the bottom. I think this is what the book is looking for. And if you look at the graph, which I have to the right there, does that make sense? Up to -2, we found out it was increasing. Sure enough, you can see here it's increasing before -2. Between -2 and 0, it's decreasing. Yep. After 1, I'm sorry, after 0, it's increasing. Yep. So nice to confirm it with looking at some graphics. Yeah, this part, it says they want you to use a computer graphics like Desmos. What do they ask you to do here? Using a computer algebra system to differentiate. Oh, to actually do the derivative? I don't know about that. But anyway, you can sketch the graphs of f and f prime on the same, find the critical. So, okay. So maybe we should, let's try doing number 66 here. I gotta write this down because I gotta change my screen. So 10 times 5 minus square root x squared minus 3x plus 16. Okay, close parentheses, and we want to do that from the interval from 0 through 5. Okay, so let's open Desmos. Let's see if I have this. So this is lesson 4.3. No, I don't have it, but that's okay. All right, so we have 10 times parentheses 5 minus square root x squared minus 3x plus 16. Okay. And what are we supposed to do here? We're supposed to do the derivative at the same time. I'll show you how to do that. Okay. So now what you could, if we call this f of x, so that function I just type f of x, I never showed you this. You can do a derivative on Desmos. You can say f prime of x. So what Desmos actually is plots in that second color. That's the derivative. Okay. So where is the derivative 0? Right here. Okay, which means this is a critical point. And sure enough, you can see it is. Because when the derivative is 0, we're at a critical point. We can see that. And where is the function increasing? It says go from, what did it say? Go from 0 to 5. So it's increasing between 0 and 5. It's decreasing from, it's increasing from 0 to 1.5, and it's decreasing from 1.5 all the way down to 5. So here's how you do that in Desmos. Besides typing in the function, you can also type in f of x equals that. And then all you have to do to get the derivative is type f prime of x, and you'll get that kind of, you'll get the derivative right then. It's really beautiful. Okay, I think we've given you a pretty Does anybody have any questions?
Nope.
The assignment, I never showed you. Core exercises 4.3. Some of you, the two of you may already know this because it's on the website, but well, it's nice just having the two of you in class, but I'm certainly hope we have a bunch of other people watching the video right away.
Mm-hmm.
I can check on that, by the way. But anyway, I hope the two of you have a very good day.
You too.
Thank you, you too.
I will see you.
See ya.
Bye.
Bye.